Space should be loud. If intelligence naturally blooms among the stars, then by now the Milky Way ought to be filled with civilizations older, wiser, and far more advanced than ours. Yet when humanity points its most sensitive radio telescopes at the sky, what we hear is nothing but the hiss of natural noise. No deliberate beacons, no obvious megastructures, no interstellar traffic jams of alien starships. In 1950, physicist Enrico Fermi crystallized this unease over lunch with a simple question: where is everybody? Today, that question is known as the Fermi Paradox, the tension between a galaxy that should be teeming with life and the stark absence of any sign that anyone else is out there. Consider this: our galaxy is more than 13 billion years old, and by reasonable estimates, a single technological civilization could, in principle, spread across the entire Milky Way in a tiny fraction of that time. Tens of millions of years, not billions. If that is even roughly true, then the fact that Earth does not obviously sit inside somebody else's empire is not just curious, it is deeply unsettling. What if everything we know about life, intelligence, and our place in the cosmos is wrong? What if we have fundamentally misunderstood how often minds like ours arise and how long they survive? Today, we journey through evidence that challenges everything. Prepare yourselves. We begin. In 1950, at Los Alamos National Laboratory, Enrico Fermi posed a question that would haunt astronomy for decades. Over lunch, surrounded by colleagues discussing UFO reports and interstellar travel, he sketched out a simple chain of reasoning. The galaxy is old, stars like the sun are common, and planets should be abundant. So where are the visitors? Fermi's rough logic has since been sharpened by detailed calculations. Even if faster-than-light travel is impossible, a civilization using sublight starships could, in principle, hop from star to star, colonizing or exploring new systems over millions of years. Studies suggest the entire Milky Way could be traversed in timescales far shorter than its age, on the order of tens to hundreds of millions of years. In the 1960s, astronomer Frank Drake encoded this intuition into the Drake equation, a framework listing factors that determine how many communicative civilizations might exist: the rate of star formation, the fraction with planets, the fraction of those that develop life, intelligence, technology, and the length of time they broadcast into space. Even with conservative guesses, the equation often yields numbers far larger than 1. So the paradox was born. If the galaxy is hospitable and intelligence is not impossibly rare, then it should be crowded with advanced societies. Yet we detect nothing. This is the heart of the Fermi Paradox. But the evidence forces us to confront an uncomfortable possibility. In the decades after Fermi, 2 revolutions intensified the paradox instead of dissolving it. The first came with the discovery of exoplanets, worlds orbiting other stars. Today, we know that planets are not rare curiosities, but the rule. Surveys suggest that on average, there is at least 1 planet for every star in the Milky Way, and potentially billions of Earth-sized planets in habitable zones where liquid water could exist. The second revolution came from astrobiology and planetary science. Researchers realized that Earth's history is not a straight line to intelligence, but a chain of improbable events, The formation of a stable, rocky world at the right distance from a long-lived star, a protective magnetic field and plate tectonics, a large moon stabilizing our tilt, and a gas giant like Jupiter possibly deflecting deadly impacts. In the early 2000s, paleontologist Peter Ward and astronomer Donald Brownlee pulled these insights together into what they called the rare Earth hypothesis. Their claim? Microbial life might be common, but complex, multicellular, intelligent life like us may be extraordinarily rare, requiring an unlikely combination of astrophysical and geological lottery wins. This hypothesis offers one potential escape route from the paradox. Maybe the galaxy is not silent because intelligence inevitably self-destructs, but because it almost never arises in the first place. But the evidence forces us to confront an uncomfortable possibility. Maybe the silence is not an illusion. Maybe it is telling us something profound about life itself. If the galaxy hosts other technological civilizations, they might reveal themselves in several ways. Narrowband radio signals, laser pulses, artificial megastructures, or unusual waste heat signatures. For decades, scientists have searched for such technosignatures and found, so far, only natural phenomena. In the 1960s, the first pulsars, rapidly spinning neutron stars, were briefly suspected to be signals from extraterrestrial beacons because of their astonishing regularity. The first detected source was even nicknamed LGM1 for Little Green Men 1. But more data quickly revealed their true nature as dense, magnetized stellar remnants. More recently, a signal called BLC1, detected by the Breakthrough Listen project while observing Proxima Centauri, briefly electrified the scientific community. It appeared as a narrow-band, drifting radiotone, exactly the kind of signal no known astrophysical process should produce naturally. Yet careful analysis showed it was an intermodulation product of human-made radio interference, an artifact of our own technology, not an alien transmitter. Breakthrough Listen, one of the most ambitious SETI programs ever undertaken, has now scanned millions of stars across wide frequency ranges using radio telescopes like the Green Bank Telescope and others. Despite analyzing petabytes of data, it has not yet confirmed a single unambiguous technosignature. In the gravitational and dynamical realm, the Milky Way's structure shows no obvious large-scale anomalies suggestive of a sprawling interstellar civilization reshaping vast regions of space. The orbits of stars, the distribution of gas and dust, and the overall galactic dynamics can be explained by known physics plus dark matter, with no need to invoke artificial sculpting. But this represents just one piece of a much larger puzzle. The silence is not just about what we do not hear, it is about what we know should be possible. Studies of interstellar colonization show that, with modest assumptions about ship speeds and colony growth, a technological species could, in principle, spread across the Milky Way in less than 100 million years, a blink of an eye compared with the galaxy's age. If even a tiny fraction of civilizations chose to expand, their presence should be unmistakable, sparkling across the sky as beacons, megastructures, or engineered anomalies. Yet surveys suggest that, on the largest scales, galaxies, including our own, look astonishingly mundane. This leads some thinkers to the concept of the Great Filter, one or more stages in the path from simple chemistry to star-spanning civilization that are extremely unlikely to be passed. The filter could lie in the emergence of life, the jump to complex cells, the rise of intelligence, the development of technology, or the ability to survive self-inflicted catastrophes and natural cosmic hazards. On the other side of the ledger, the rare Earth hypothesis systematically catalogs the ways Earth might be special, a position in a relatively calm, galactic habitable zone away from destructive radiation near the galactic center, a star with stable output, a planet of the right mass to hold an atmosphere and sustain plate tectonics, a large moon stabilizing axial tilt, a protective magnetic field, and a gas giant like Jupiter that may reduce catastrophic impact rates. Each factor alone might not be rare, but combined, they could make Earth's circumstances extraordinarily unusual. Some versions of the hypothesis emphasize events like the giant impact that formed the moon, the rise of oxygen in Earth's atmosphere, and the Cambrian explosion of complex life as low-probability steps that may seldom be repeated. Recent work in astrobiology and planetary science has continued to explore how finely tuned some conditions for long-term habitability might be, such as the need for long-lasting plate tectonics to regulate climate over billions of years, or the importance of a stable climate window for complex ecosystems to evolve. The evidence extends beyond the raw number of planets into the realm of how many can truly nurture minds like ours. The Fermi Paradox can be framed around two broad possibilities. Either intelligent life is rare, or it is common but almost always transient or hidden. The rare Earth hypothesis occupies the first camp, arguing that Earth's chain of enabling conditions is extraordinarily unlikely to be replicated. In this view, the galaxy may be richly populated with microbial life, simple cells eking out existences in subsurface oceans, on temperate exoplanets, or even beneath icy crusts. But complex, multicellular, tool-using intelligences are vanishingly scarce. Humanity, in this framing, might be among the first, or even alone, at our level of technological capability in the Milky Way. On the other side, hypotheses like the Great Filter suggest that many worlds may start down the path to intelligence, but very few cross one or more catastrophic thresholds. Some filters are backward-looking. Perhaps the jump from simple to complex cells is extraordinarily rare. Others are forward-looking. Perhaps technological civilizations often destroy themselves through warfare, ecological collapse, or runaway technologies before they can expand beyond their home systems. Social science perspectives add that a civilization's choices, values, and risk management strategies could be as decisive as their physics. A species might master fusion power and artificial intelligence, yet fail to coordinate globally enough to avoid self-inflicted disasters. A world might develop radio technology, but never pursue large-scale interstellar expansion, choosing virtual realities, sustainability at home, or tightly controlled non-expansionist norms. This forces us to reconsider fundamental assumptions about progress, inevitability, and the idea that advanced always means expansive or loud. Perhaps the cosmos is not empty, but mostly quiet by design, by accident, or by widespread failure. The Fermi Paradox can be framed around two broad possibilities. Either intelligent life is rare, or it is common but almost always transient or hidden. The rare Earth hypothesis occupies the first camp, arguing that Earth's chain of enabling conditions is extraordinarily unlikely to be replicated. In this view, the galaxy may be richly populated with microbial life, simple cells eking out existences in subsurface oceans, on temperate exoplanets, or even beneath icy crusts. But complex, multicellular, tool-using intelligences are vanishingly scarce. Humanity, in this framing, might be among the first, or even alone, at our level of technological capability in the Milky Way. On the other side, hypotheses like the Great Filter suggest that many worlds may start down the path to intelligence, but very few cross one or more catastrophic thresholds. Some filters are backward-looking. Perhaps the jump from simple to complex cells is extraordinarily rare. Others are forward-looking. Perhaps technological civilizations often destroy themselves through warfare, ecological collapse, or runaway technologies before they can expand beyond their home systems. Social science perspectives add that a civilization's choices, values, and risk management strategies could be as decisive as their physics. A species might master fusion power and artificial intelligence, yet fail to coordinate globally enough to avoid self-inflicted disasters. A world might develop radio technology, but never pursue large-scale interstellar expansion, choosing virtual realities, sustainability at home, or tightly controlled non-expansionist norms. This forces us to reconsider fundamental assumptions about progress, inevitability, and the idea that advanced always means expansive or loud. Perhaps the cosmos is not empty, but mostly quiet by design, by accident, or by widespread failure. While philosophers debate, astronomers keep listening. Projects like Breakthrough Listen have dramatically expanded the search space, scanning billions of frequency channels across large swaths of sky. Recently, researchers deployed advanced artificial intelligence systems using powerful accelerators to comb through radio data up to hundreds of times faster than before, allowing real-time detection of fast radio bursts and potential technosignatures buried in noise. At the same time, new radio and optical facilities are coming online or being planned. High-frequency technosignature searches with instruments like the Sardinia Radio Telescope are probing previously unexplored bands, looking for narrow-band drifting signals in regions such as the galactic center and fields containing thousands of stars. Future observatories, both ground-based and space-based, will further widen the spectrum and volume of space probed. On the planetary side, missions and telescopes focused on exoplanets aim to study Earth-like worlds in unprecedented detail. Upcoming facilities are being designed to detect atmospheric biosignatures, gases like oxygen, methane, and combinations that might indicate biological activity on planets tens or hundreds of light-years away. If Earth-like atmospheres turn out to be extremely rare, that would bolster the rare Earth picture. If they are common, the paradox deepens. Recent breakthroughs suggest a rapidly approaching era where we may routinely catalog not just exoplanet sizes and orbits, but their climates, surface conditions, and potential habitability markers. In parallel, work in planetary geology, climate modeling, and comparative planetology continues to test which of Earth's special traits truly matter for long-term complexity. What this means for us is stark. If the rare Earth hypothesis is broadly correct, humanity may shoulder an outsized share of the universe's capacity for self-aware reflection. Our decisions about technology, environment, and long-term survival could influence whether intelligent life in this galaxy becomes a brief flicker or a sustained presence. The most profound implications emerge when we consider what the Great Silence says about reality itself. If Earth is a statistical outlier, a rare convergence of favorable conditions in an otherwise indifferent cosmos, then our existence is both fragile and extraordinary. One possibility is that the Great Filter lies behind us. Perhaps the emergence of complex cells, multicellularity, or technological intelligence is so improbable that it has occurred only once in our galaxy. In that case, the silence is not ominous. It is simply the echo of almost universal failure to reach our stage. Another, more unsettling possibility is that the Great Filter lies ahead. Perhaps it is relatively easy to reach our current level, but extremely difficult to survive long enough to spread to the stars. Nuclear war, uncontrolled climate change, engineered pandemics, or misaligned artificial intelligence could serve as filters, challenges that most technological civilizations do not overcome. There is also a quieter option. Maybe advanced civilizations often choose not to broadcast or expand. They might encrypt all communications, use tight beam transmissions we are unlikely to intercept, or migrate to energy-efficient computational substrates that emit minimal detectable waste heat. In such a scenario, the galaxy could be full of introspective, non-expansionist minds, all but invisible to crude searches. Speculative but scientifically grounded ideas even suggest that we might be in an observational selection effect. Intelligent beings will, by definition, find themselves on worlds where conditions allowed intelligence to arise. That does not mean such worlds are common, only that anyone asking the question must inhabit one of the rare success cases. This anthropic reasoning dovetails naturally with the rare Earth hypothesis. The most disturbing implications arise when these threads intertwine. If complex life is rare and the future is dangerous, then humanity might be both a cosmic exception and balanced on the edge of a cliff. Our success or failure in navigating the next few centuries could determine whether the Milky Way ever awakens into a network of communicating civilizations or remains silent for eons to come. We began with a deceptively simple question: where is everybody? From Fermi's lunchtime insight through exoplanet discoveries, technosignature searches, and the rare Earth hypothesis, the evidence has painted a picture stranger than many expected. A galaxy full of planets, but so far empty of clear voices. The current scientific consensus is cautious. Most researchers agree that microbial life may be common, but complex and technological life could be rare, and the absence of evidence is not yet evidence of absence. Large, systematic searches are only a few decades old, and the region of search space actually explored across frequencies, sky positions, timescales, and message types is still a tiny fraction of what is possible. Yet even this early silence reshapes our understanding. It suggests that intelligence is not an inevitable cosmic destiny, but a fragile, contingent outcome. It reminds us that Earth's long chain of good fortune, its stable star, protective magnetic field, active geology, and long climate stability may be the exception not the rule. If humanity is one of the universe's rare windows through which the cosmos can know itself, then our responsibility is immense. Our task is not only to search, to listen, and to explore, but also to endure, to survive our own potential filters, and perhaps one day to transform the great silence into a chorus. The universe is vast. The mysteries are endless. The journey continues.